Good afternoon, ladies and gentlemen. My name is Panos Ikonomo. I represent Mediterranean Acoustics R&D. We are the developers of one-to-three-lab terrain and outdoor sound propagation software application. And I will be presenting a paper, a comparison of ISO 9613 Part 2 with advanced calculation methods as they're implemented in our product. We're going to be looking at predictions versus experimental results. I have been a consultant for 30 years now, and on many occasions my predictions did not match my measurements, something which I found unacceptable. Therefore, I decided to do something about it. In 2009, I have established the Mediterranean Acoustics Research and Development in order to be able to develop tools, accurate tools, to offer to our community. Late 2011, we have asked on LinkedIn members of the Institute of Acoustics and members of the Acoustical Society of America, which method do they use usually for their sound, outdoor sound propagation? And more than 50% replied ISO 9613 Part 2. The other methods on the poll were Nord 2000, Harmonise from Kawi, and others. And from those methods, we consider Nord 2000 and Harmonise as advanced calculation methods that are nowadays implemented in user-friendly software packages. Based on that feedback, we decided we were going to implement ISO 9613 Part 2 in our product with the next update. May I take this opportunity to ask how many of you use ISO 9613 Part 2 in this room? Yeah. So LinkedIn poll was correct. More than 50%. So, why is ISO 9613 Part 2 the favorite method? This is a question you might be able to help answer after the presentation of results, maybe perhaps during a brief discussion after the presentation. Let's talk about standards and independent research, the latter being what we do. Standards provide the same answers, irrespective who's the user. In my opinion, the downside is that they are being perceived as dogma and often provide inaccurate results. Nevertheless, they produce widely accepted algorithms. Independent research is like detective work with lots of twists and turns in the plot. To me personally, it's a great fun and mentally rewarding to do research. And it needs intuition and a stomach to be able to handle the ups and downs of the work. It also produces unique algorithms, possibly less accepted by the public, the community. Software based on standards provide simpler code, fast and approximate results, whilst software based on research provides complicated code, slower and yet more accurate results than software standards, based on standards. What follows is a theoretical background on our product, a bit on the ISO method, presentation of results, comparison of results, discussion of results, and hopefully some conclusions. OTL terrain, olive tree lab terrain, is based on the work of Solomon's very model using analytical solutions. Pattern and Pierce for spherical wave diffraction coefficients. Chessel for spherical wave reflection coefficients. Delaney and Baisley for finite surface impedance. I know that there are much better models for parameter models, but for the time being, this is what we apply. On play on finite size reflectors with Fresnel zones. Keller on his geometrical theory of diffraction. We use a unique sound path explorer, an in-house model which is able to detect and draw diffraction and reflection paths in a pure 3D environment. For the time being, as far as atmospheric turbulence is concerned, we're using harmonize. We're hoping to replace this model, and I bet a very good source would be a book called Predicting Outdoor Sound by Attenborough, Poroshenkov, and Lee, which I strongly recommend. It was a source of inspiration and lots of information. Let's say a bit about the ISO method. Everybody knows it's an empirical method adopted as a standard in 1996. It lends itself for spreadsheet calculations. There were good reasons at the time, in my opinion, to apply such a method as a standard, simply because things were difficult at that time with technology. But there's ambiguity in its implementation. Therefore, two different users might come up with different results. Right, so we're going to be looking at some comparisons, some comparison results among terrain, the ISO method, and published measured data. The published measured data we have used is the one that was used to validate NOR 2000. We have selected 8 cases from a great number of cases based on distance, with and without barrier, and different types of barriers in between, and also on simplicity, simply because we need to understand the mechanisms involved in the outdoor sound propagation, and also for ISO 9613 Part 2 to be able to handle it, because ISO does not handle all cases. What we're seeing is distances of source receiver between 4.5 meters up to 120 meters, with or without barriers in between. The results are going to be presented in terms of excess attenuation, the transfer function, which is effectively the effect of the environment on what the environment does to the direct sound at the receiver point. I know it looks a bit crowded, but there is a reason for it, because if one is able to visualize the results in 3D, one is able to have a better judgment as to what's going on, especially about the mechanisms involved. We see the results in black dots. We see the measured data in 1/3 octave bands. The blue curve, the terrain results in 1/3 octave bands, and the red curve is the ISO results in 1 octave bands. On the right, we see the geometry. Bottom left, we see sound paths between, possible sound paths between source and receiver. And on the other slide, pictures on the slide, we either see mapping of excess attenuation on vertical or horizontal planes of either ground or barrier, or we can see the pressure before and after the insertion of a barrier. Okay, let's go to the first case, which is a simple case between, which involves a source and a receiver over a ground at a distance of 4.5 meters. As you can see, the predictions with terrain coincide very well with the measurements, whilst the ISO, which is the red curve, seems to be ignoring all interference effects with the ground. We can see on the left the reflection off the ground. In the middle, we can see mapping on a horizontal plane of the broadband level. And on the right, we can see the beautiful interference effects at 10 kilohertz, just to show how things work. Again, the same geometry in the next case, which is the only difference, we have a thin barrier in between source and receiver. Again, predictions with measurements in terms of terrain, I would say there's a fair match, whilst the ISO seems to be ignoring the interference effects. On the left, we can see the sound paths between source receiver. In the middle, we see mapping on a vertical plane behind the barrier, and here we can see the mapping on the horizontal plane across the barrier. More or less the same geometry. The only difference now, we have a thick barrier in between. We have a fair match between terrain and the measured data, but again, ISO seems to be insensitive to any changes happening. We see the sound paths, and we can see sound pressure level in the middle before the insertion of the barrier and the sound pressure level after the insertion of the barrier. The barrier is shown just to be able to visualize where it's located. Again, the same geometry, but the receiver is just a bit lower as the ones before. But now we have two barriers, thin barriers in between them. And here, I would say we have a discrepancy between our predictions with measurements. I'm going to come back to this case to talk about it a bit more later. We see sound paths, reflections, diffractions, up to third order diffractions between source and receiver, mapping on the horizontal plane, side view, and top view. We move to a case which we have a source and receiver at 120 meters apart, and there is a hill in between them that could be simulated as a thick wedge barrier. Again, I would say there is a fair match between longitudinal terrain and measured data. The ISO deviates again from measured data. Before and after the insertion of the barrier, if one can move the hill. Here we have a source and receiver in between and on just ground, and I would say we have good match between the terrain results with the measured data, but ISO miscalculates the interference effect. And again, we see mapping on vertical planes. The last two cases are similar. The source and receiver have a distance of 50 meters in between them, and there is a thin barrier right in the middle. Fair match between predictions and measurements with longitudinal terrain. The red curve is the ISO curve. There is it seems to be trying to at least follow the trend of what's happening, but there are deviations again. I show these pictures at the bottom because they are beautiful in terms of color and shape. And it's a horizontal mapping above ground at 10,000 yards. The next case, instead of a thin barrier in between, we have a wedge barrier. Again, a fair match between predictions. ISO still seems to be deviating, even though there is a trend. Similarity there. Sound pressure levels before and after.